Okay, so last time we introduced the problem of matrix multiplication, and in fact we also gave these 7 products of Strassen. So P1, P2 to P7. So these are products not of just 2 variables but actually 2 linear forms. Left is in X matrix and right is in Y matrix. So there are 4 X's and 4 Y's. And when you compute these products, you have to take care of the order, because remember that X11 may itself be a matrix and Y11 may itself be a matrix. So that product is actually non-commutative. So P1 is exactly that. It is not the reverse. You cannot do Y11 plus Y22 times X11 plus X22. It's exactly in this order. And with that, you can actually check that X dot Y will be this, without using commutativity of Xij and Yij. So today we will finish this formally the proof of Strassen that matrix multiplication takes n to the log 7 operations, where the ring R is where the entries of the matrix come from, of the n cross n matrix. Any questions? Okay, so X and Y are n cross n matrices over R. We are assuming n to be a power of 2. So proof will be an induction on L. Okay, so we will compute how many multiplications and how many additions in the base ring R are required. So we will show by induction on L that we can do matrix multiplication in 7 raised to L R multiplications and that many R additions. So actually both multiplications and additions are not too many. This is n to the log 7. That's the order. So base case is L equal to 1. Right, so these are 2 by 2 matrices which we have already done. So for L equal to 1 you got 7 multiplications and 18 additions, right? That is the base case already. That was actually the starting point of all this. The induction step is L minus 1 to L, where L is at least 2. Right, so how do you take this one step? So this will be the block structure application. So you look at x11, x12, where these xij's, yij's, zij's, they are 2 raised to L minus 1, cross 2 raised to L minus 1. And the full matrix is 2 raised to L cross 2 raised to L. Right? So for n cross n matrix, you are looking at the block structure n by 2 cross n by 2. And so this n by 2 multiplication of matrices, multiplication of n by 2 by n by 2 matrices, this you do inductively or in the algorithm recursively. So these are 2 raised to L minus 1 cross 2 raised to L minus 1 matrices. So there are two things. One is when you have to multiply xij with or xik withykj, that multiplication you will do recursively. And assuming that, so that is the recursive part, and this also will require then this 2 cross 2 matrix multiplication. For that you use Strassen equation. So, well, I think look at this, look it into two steps. So first is use Strassen equation here. And the entries of these matrices are in which ring? So that is n by 2 cross n by 2. So n by 2 cross n by 2 matrices over the ring are obviously also form a ring. So you do this 2 cross 2 matrix multiplication over this ring using Strassen's equations. But that in the end will require you to multiply two such matrices, right? Like this x11 plus x22 times y11 plus y22 was p1. So that multiplication you will do recursively. So do that in those two steps. And now, so the algorithm, is it clear? Right, so it's a recursive algorithm using Strassen's equation. So now you solve, you analyze the time complexity. So that will finish your induction step. So what is the number of R multiplications? So R multiplications that you are doing, so that is 7 to the L minus 1, many multiplications. Right, that is for n by 2 times n by 2 matrices. And how many such multiplications you are doing in the induction step? That is given by Strassen's number, which is 7. So that's 7 to the L, which is the correct value in the to go to L. And look at number of R additions. So that number was 6, 7, L minus 1, 4 L minus 1 by the induction step. And how many such additions are needed? So let me write the expression first. So I am giving it in two parts. This first look at 18 times 2 raised to L minus 1 square. Right, what is this? So these are the 18 additions which you do in Strassen itself. Right, that is the number 18. And all those are n by 2 by n by 2 matrices. So that many ring R additions. What is the first part? The first part is for the recursive calls. You are making 7 recursive calls, and in each recursive call that many additions. And this is in Strassen's equation. Okay, so that's the overall additions you need in the base ring R, which you can see is as required in the induction step. Okay, so the second part is 4 to the L minus 1 times 18. So that you will subtract 21 from 42 from that. The first term is, main term is 6 times 7 to the L. Is that clear? So overall we have shown seven to the L ring operations, which is n to the log 7 to base 2. Okay, that is Strassen's matrix multiplication theorem. But you have precise expressions for multiplications and additions in the very base ring. Any questions? So, yeah, one could already be happy with this. This will give you some advantage if you take bigger and bigger matrices, bigger and bigger n. So it's a surprising algorithm, improves over n cube. So this is now n to the 2.8. Right, but the question is, why did this algorithm exist? Right, so by definition it should have been n cube. Why did it reduce to n to the 2.8? So that study is still ongoing. So after decades of work, the current best for matrix multiplication is n to the 2.37 28639. Okay, I give you 7 digits because each of these digits people have worked very hard to improve. So there are at least 7 papers, and there are at most 50 papers on matrix multiplication. They all trying to improve each and every digit here. Okay, so slowly 3 has been reduced to something like 2.37. So this is from 2014 from Lagol. So that survey paper, if you want, you can read. And currently there are no good techniques to improve this. Whatever techniques have brought it down to this are more or less stuck. Nevertheless, the conjecture is that, sorry? Exactly. So the conjecture since the time of Strassen has been that matrix multiplication has complexity. N to the 2 plus epsilon for whatever epsilon you want, for any positive epsilon. Right, but this is still, there is a gap in the current understanding. So there is still a gap of 0.37. Note that you cannot do better than this because your input size is 2n square. Right, so you can never improve on n square, and your output is also n square. So you can never improve on n square. So that's really asking for too much. Yeah, after this log 7, things become quite complicated. So that will take several lectures if we want to improve over log 7 to anything. Okay, so instead of attempting that, uh, we can just see the concepts which go into improving log 7, because that concept is also helpful in other places. It's a fundamental concept in algebra. So you want to understand the exponent of matrix multiplication. So let's denote the exponent by omega, not to be confused with omega we were using before, the root of unity. So this omega is just a number expected to be something somewhere between 0 and 2.37 to 2.37. So it is known that omega is between 2 and 2.37 28639. Actually, we are talking about the limit, so we can also call it 2. This 2 just means that you can go arbitrarily close to 2 but never reach it. So that limit is what we are calling omega. So all the known upper bounds on omega use something called tensor rank. Okay, that's the algebraic concept which you want to now introduce. So have you heard about tensor rank? It is also used in artificial intelligence and ML applications. With tensor decomposition, what is that? What is the simplest example of tensor rank?
Matrices.
Yeah, matrix rank is the simplest example of tensor rank. Matrix rank is just order 2 tensor rank. So matrix is actually an order 2 tensor. And then you can keep on growing the order. So when you go to order 3 tensor, it's a matrix in 3D. Very explicitly. That explicit representation actually has no use, but if you want to just look at the extension of a 2-dimensional matrix, then it's a 3-dimensional matrix. So a notion of rank for that is complicated. So for matrix, rank is kind of a unique definition which is very useful everywhere, but for order 3 tensors that is not true. So there are multiple definitions and neither of them are very helpful. I mean, questions there are all open questions. So order 3 and beyond it becomes complex. So this omega is also related to some tensor rank. So let us first define an order 3 tensor whose rank omega is. So let's directly go to the definition. So let us define a tensor, or in fact tensor motivated by matrix multiplication. So that is called the matrix multiplication tensor. Okay, so this tensor you can think of as a 3D matrix if you want to see it explicitly. So, but I want to see it as a polynomial. So MM tensor is a polynomial in many variables. So I'll call them big X ij, y ij, z ij. ij 1 to n. So the polynomial itself looks like this. So we'll call it T and R. So if you have seen the definition of this, what is that? The tensor polynomial for matrix multiplication is so it is directly inspired from the definition of matrix multiplication. So it will look like x I k y k j z I j. Okay, so definition of the tensor lives in a completely different place from matrices. It's roughly there are roughly n square many variables xij, yij, zij's, and in these roughly 3n square many variables you have this cubic polynomial. Okay, this cubic polynomial T n comma r. In this, if you look at the coefficient of zij, then you will see an expression which is similar to the expression for small zij that you saw in matrix multiplication. Okay, so that is the connection, or that is the relationship between this definition and matrix multiplication definition. But we are doing very different things here. So we have defined this cubic polynomial. So its degree is 3. And it has many variables. So for example, if you look at the matrix multiplication tensor for 2 by 2 matrices, so it is Z11 plus then Z21 plus the last is Z22. Okay, so there are exactly 3 times 2 square many variables. Yes. Is it? We don't want it to be ordered.
And also we need an extra condition for k to be in between I and j.
No. That is not the case in matrix multiplication. K varies from 1 to n.
But why?
Yeah, cubic polynomial and 3n square variate. That's true. Any questions? And so then for 2 by 2 matrices, you can see that there are 12 variables, 3 times 2 square, and you have these cubic monomials in x, y, z, and you have 8 of these monomials.
So what is the connection of these two matrix multiplication?
Yeah, I know you want to hurry. We are going there. So once this definition is there, let us look at the rank of this tensor. So rank of a tensor in general and this tensor in particular, the most common rank defined is you want to decompose this tensor into sum of simple tensors. By a simple tensor, we would mean one where you are just multiplying linear forms. So a linear form in x times a linear form in y times a linear form in z. Okay, for example, x11 times y11 times z11. This is a simple tensor. This tensor is called rank 1. So you want to decompose your tensor into a sum of simple tensors. The minimum number of these simple tensors is called the rank. Okay. So I'll give you the formal definition afterwards, but with that in mind, what is an upper bound on the rank of tensor T to R? How big can that rank be? Can it be 9? Yeah, already just by brute force you can see by definition T to R is a sum of 8 monomials, right? So its rank cannot exceed 8. 8 is the maximum. But you are not sure whether it's actually 8. It can also be 7. And it was Strasson's imagination that he actually gave a decomposition where it's 7. Okay, and there is also a proof that it's not 6. So the rank of this tensor is exactly 7. Okay, that is the reason for log 7. So rank of tensor T is the least number R such that there exist linear forms. So Li, which is purely in terms of x variables, then Mi, which are purely in terms of y variables, and Ni purely in terms of z variables. So these are linear forms. I will range from 1 to R. And all this data has to satisfy the following equation. The tensor is decomposes as Li times Mi times Ni. Okay, so rank of a tensor. So this now you can see that it's a pretty general definition. It doesn't have anything to do with matrix multiplication tensor. There is no need to restrict to matrix multiplication tensor. You can look at any polynomial in clearly demarcated variables. So family X, family Y, family Z. And you can ask the question whether that polynomial, your polynomial, can be written as sigma Li, Mi, Ni. So this is the rank of an order 3 tensor. And if you have order 4, then you will have 4 variables in the partition. So you will have, let's say, V bar, X bar, Y bar, Z bar. And then you have to decompose it into product of 4 linear forms. Okay, so maybe Ki, Li, Mi, Ni. So this is the general concept of tensors, tensor decomposition and rank. So this is a simple or rank 1 tensor. So you want to decompose your tensor into few simple tensors. If you cannot decompose into few simple tensors, then your tensor is hard. Okay, that is the understanding. But it is also true that in life it is hard to find hard tensors. Okay, so this is not an easy problem to come up with a polynomial and show that its tensor rank is high. So these are classic lower bound questions, and mostly they are open questions. Yeah, actually examples are not there. An explicit polynomial with high tensor rank. Uh, that's an open question. No, before we jump to permanent, this class may not know it. Something even simpler is, or what is the meaning of order 2 tensor rank, right? That's an instantiation of this or specialization of this. So order 2 tensor, let's say you have some tensor T in 2 families of variables x bar, y bar, and you want to write it as sigma Li times Mi. So this is a polynomial in x bar, y bar. So for a polynomial T x bar comma y bar, and the tensor rank to be defined this way, smallest r, can you see that this is just matrix rank? What is the matrix here? For this order 2 tensor T, how will you define the matrix? Or for a matrix, how will you define T? Equivalently, so you are given a matrix. How do you see it as a tensor, order 2 tensor polynomial? So I claim that these two theories are the same at order 2. Tensor decomposition, tensor rank is the same as matrix rank. Okay, but what is matrix decomposition that we are talking about? So that equivalence I leave as an exercise. So what is the relationship with matrix rank? So it would be a specialization of this much more general theory, but we are not there. So we are actually now at order 3 tensors, and we are looking exactly at matrix multiplication tensor. So let's move forward with that. So the rank of matrix multiplication tensor for n cross n matrices over R ring R, this is at most how much? N cube, right? That's by definition. And it is at least how much? Yeah, the at least part we have not given a proof yet, but you can show that it's n square. So how will you show that? So less than equal to n cube is simply by definition of rank. Greater than equal to n square you can show by, so you can express, if you can express T as a sum of only n square many, or let's say n square minus 1 many, Li, Mi, Ni, then show that you can essentially make all these products 0 by fixing the variables, while the tensor will not be 0. The reason for that is that in your the variables, each of the variables x, y, z family has n square many variables. So intuitively, if you set n square minus 1 variables to 0, still something remains. Okay, not the whole tensor vanishes. So it's by fixing variables. Fixing variables in T and R gives a contradiction. Yeah, I won't go into the detail of this. You can do it as an exercise. It's not very important. More important is the connection between rank and matrix multiplication. Let me make the following claim, that matrix multiplication for n by n matrices can be done in the rank of this tensor many multiplications. And that is a very useful thing to know, because if you decompose your tensor into few products, simple tensors, then you also get an algorithm for matrix multiplication. Specifically for n cross n matrix multiplication, you get a faster algorithm, and then using the block structure, you can generalize it. In fact, that is what you did for n equal to 2. So what is the proof of this? Z equal to 1.
All the zi's,
Yes, so you look at the definition of the tensor and these Li, Mi, Ni. So say you have a representation of T into few products. So in this, in particular, look at Ni z bar. So these are the variables z11 dot dot znn. So extract the coefficient of z11 from here. So if you extract the coefficient of z11, you will see that on the LHS, you would have that matrix multiplication entry of z11. Matrix of the matrix Z, you will have z11 entry. On the RHS, what will you have? You will have a sum of few LI-MI products, right? So you have kind of Strassen's equations that you multiply R many LI-MI, and from those products, a linear combination gives you the first entry of matrix multiplication, matrix product. Now you try to extract Z12. So compare the coefficient of Z12 on both sides of this equation. And again, you will see that same products, R products, their linear combination gives you the second entry of matrix product, and so on. So it just follows from this equation. It's already tailor-made. The products Li times Mi R of these are enough. Okay, so for 2 cross 2 matrix, this is what Strassen did essentially. Uh, that he first wrote T as a sum of 7 products instead of 8. So that was saving one product. And then by extracting these coefficients Z11, Z12, Z21, Z22, you get all these 4 expressions in terms of 7 products. And the same thing in general will work. You will only have to do R multiplications, little r multiplications in the base ring. Is that clear? Okay. And this proof, so what is the converse of this? That if you can do matrix multiplication in let's say R prime many products, what can you say about the tensor rank of the tensor? It's the same proof. You get then a decomposition with R prime simple tensors. Right? So this equation actually is a tight connection between how many multiplications are required for matrix multiplication and tensor rank. Okay, so the tensor rank of T2 is 7. Okay, this is another way to read Strassen's complicated equations. It's just showing that instead of 8, it's 7. So, I mean, it is conceivable that you compute tensor rank of now T3 comma R and then T4 and T5 and so on, and at some point you get something better than log 7, right? So that would be a simple-minded way to improve matrix multiplication.
Strassen equation only shows it is less than equal to 7.
Yeah, but you can show that it's greater than 6. That's a separate proof. So we can maybe write less than equal to here, but it's known that it's 7. It's not less than this.
For the converse, will we always get linear form?
Yeah, so when we say multiplications, yeah, so technical term for that is we want to count the bilinear complexity. So bilinear complexity means that given this matrix X and matrix Y, we are only allowed to multiply linear forms. So nothing fancier than that is you are allowed to do. That is actually a reasonable assumption because ultimately you have to compute Z matrix whose expressions are only bilinear expressions in X and Y. So maybe you are confusing or you are thinking about circuit complexity, but this is not that advanced. This is only looking at products which are quadratic in X and Y. Yeah, so you can try to do that, but believe it or not, this becomes very hard even for T3. So to compute tensor rank of T3, the problem is that you have this tensor polynomial has how many variables? 27, right? So it is 27 variate cubic polynomial, and so when you will try to discover Li, Mi, Ni, these are all linear functions in 27 variables. So there is a huge number of unknowns for the coefficients of Li, Mi, Ni, and if you try to do this by hand, which means you program and you use supercomputers and all that, you still cannot make it work. Even with the current computation, it's a very hard problem to actually find Li, Mi, Ni, and hence R. So this is still an open question. Even for T3, this is unknown. So obviously you know that rank of T3 is at most 27, but we don't know its exact value. After a lot of work, what is known is that this is between 19 and 23. Okay, so it is at least 19 and it is at most 23, which is an improvement over 27. But still 19, 20, 21, 22 to 23, amongst these 5 values, there is still a confusion. Okay, with all the computational power, this is open. So that is in practice. Theoretically, there is a good explanation for this. So Hastad showed that tensor rank computation for even for order 3 tensor so tensor rank decomposition, or actually I should say computation, is NP hard. So if you are looking at a general order 3 tensor, which means it has n variables, then as n grows, this is an NP hard problem. Okay, so in general you can never solve it in a reasonable amount of time. What can you say about order 2 tensor rank computation? How hard is that? So that we claimed is just matrix rank, right? And matrix rank you can compute very efficiently. So order 2 tensor rank computation is very simple, but order 3, when you go to order 3, it becomes NP hard immediately. Okay, and forget about higher orders. That is just harder. Those are the important points. What is the exact connection between matrix multiplication exponent and the rank? So that you can deduce. So if the tensor rank for n0 is R0, then what can you say about omega, the matrix multiplication exponent, right? So that will be log of R0 base n0. That's the exact relationship. So for T2 you have shown 7, so it gave you log 7 to base 2. If for some bigger n0, say you go to 10 by 10 matrices or 100 by 100 matrices and you come up with a magical algorithm or magical tensor decomposition with a very small R0, right? So then you may improve omega. This log of R0 base n0 may be less than the best known. Okay, yeah, that's it about matrix multiplication. Any question? Okay, in other than Strasson's algorithm, or the improvements on Strasson's algorithm have come not by directly working with this T and R, but tensors related to this. Okay, so T and R is still not understood, but there are some other tensors which are related to T and R, and the tensor rank for those are bounded, and those bounds improve omega. Okay, so there is a whole list of such complicated tensors, but they are still there are ways to study them in contrast to T and R. So that is what these matrix multiplication papers do. Yeah, but we will not study that. Okay, then we can move on to the new topic. Uh, so I hope you have now enough experience in multiplying things, right? Be it numbers, polynomials, matrices. So now is the time to factorize, the opposite of multiplication, and that is a real task. Okay, so we'll start with factorizing polynomials because this is the simplest. Integer factorization is so hard that all your security is based on that currently. So we'll start with first with polynomial factorization. So do you know any algorithms for polynomial factorization? Have you seen any ways to factorize polynomials, or which special case is finding roots? So what are the algorithms for finding roots? Yeah, so you must have seen only one algorithm, which is Newton iteration or variants of it, right? But that gives you approximate roots. So what if you want to find exact roots? So we'll actually not discuss, for now we will not discuss Newton iteration, we will discuss very different methods. Because we actually want exact roots, especially when you are over a finite field. So if you are over a finite field, then Newton iteration actually, I mean, it's a symbolic computation algorithm, so you can implement it, but it loses its geometric meaning, right? Because in a finite field, you can't really, you cannot really draw a genuine picture. It's a discrete domain, not a continuous domain. So we'll start with the finite fields. We want exact algorithms, not approximation. Yeah, it's Newton iteration. It works in many cases. I will not say it doesn't work. With moderate assumptions, it will work, but the geometric pictures will all be false. So it will be the classic case of drawing wrong pictures but getting correct algorithms. That also we will do in this course, but for now we will start with exact algorithms. So the exact problem is you are given a, let's start with univariate polynomial over some field. Field is f, big F. This little f polynomial is of degree d. So you want to compute another polynomial gx in the same field of degree 1 to d minus 1. Okay, so its degree should be less than that of f, and it should at least be a linear polynomial. It should not be a constant, such that g divides f. Okay, this is the question. So in simple terms, f is given and you want to find a non-trivial factor g. And non-trivial means that it should not be a constant, it should be at least linear. So degree 1, and it should not be the full thing, so it should be degree d minus 1. And we want to do this we want practical algorithms for this. So which means that it should your algorithm should be in poly D many F operations. Okay, so in terms of base field F operations, your algorithm should be very fast. So this is the exact factor finding. Why do we pick field? We only want to look at polynomials over a field because there you know that there is unique factorization, right? So unique factorization would in particular mean that the number of factors is the number of irreducible factors is at most D, right? So D is in the input, so you can basically output all the factors. So you don't just have to find one factor, but once you have an algorithm to find one factor, you can find all factors, right? So all these things are efficient then. So Fx is a unique factorization domain. So that is each Fx product of Fi, Ei uniquely, where Fi's are irreducible. And EIs are just numbers. They are non-negative numbers, and FIs are irreducible polynomials. So this UFD means that F will always have this list of FIs will be unique, and the list of EIs will also be unique. And if you compare the degree both sides, then this means that FIs can at most be D many. In fact, sigma EI is at most D. So Fi, where Fi is irreducible and they are co-prime. So they are mutually co-prime. That's also important. Okay, any question? Yeah, that's a fact. Now you can actually prove it because you have seen GCD, etc.
PID.
Sorry?
The PID certainly.
Oh, everyone here may not know PID. Yeah, but by first principles you can prove this, which is use GCD algorithm. And so if there is a different factorization product GI EI prime, then you can argue that GI has to be some Fj. If it is not, if it is co-prime to all the FIs, then you can take GCD and so on. So I will not go into the proof, but it can be proved by first principles. This is a pretty standard result. Division algorithm.
If he gets a ED, then ED is
What's an ED?
a Euclidean domain.
Yeah. So it's ultimately Euclid GCD.
Yes.
So Euclid GCD also used only division. So all these things are related. So you can use any method, whatever is you find comfortable in.
Irreducible then they're co-prime.
Sorry.
If the factors are irreducible,
Uh-huh.
they will be co-prime.
No, I mean they may be proportional. One may be F, the other may be 2F. some unfortunate things. So factorization pattern of course depends on the field. And so do factorization algorithms. They heavily depend on the field. So do its algorithms. Right, so which is why we'll actually have several subtopics in this main topic of polynomial factorization. Each subtopic will look at the specifics of the field. Okay, so we'll at least have 3-4 parts of polynomial factorization. So it's a long topic in this course. But the byproduct of all these subtopics will be huge. So the byproduct will have applications, has applications in diverse areas in computer science and in math. So example is that if you look at the polynomial x square plus 2, right? So over Q it is reducible or irreducible? So why is it irreducible?
Otherwise, it would have had a root.
Yeah, which is square root of minus 2. So you have to show that square root of minus 2 is not in Q. Right, that's again a small proof. So do that proof. Why is square root of 2 irrational? So by that proof, you know that x square plus 2 is irreducible. Over Q it is irreducible, but if you go to some other field, like go to a finite field, say mod 3, then it will be so over F3 I'll call it. It will factorize because there plus 2 is minus 1 and then it factorizes. So x square plus 2 is the same as x minus 1 times x plus 1. In fact, it has two distinct roots. And mod 2 it is worse because mod 2 it is just x square. So it has a repeated root. Okay, so the multiplicity of the roots, where the roots are, how the factorization is, everything is dependent on the field. So do you know a field where every polynomial factorizes? Right. So this is another fundamental theorem in, is it in algebra or analysis? One of these two, proven by Gauss. That over complex, every polynomial factors. Do you know the proof of this? When I say polynomial, I mean univariate polynomial, right? We are only looking at univariate. So every polynomial factors, which means to what extent it will factor? It will factor all the way to degree 1, right? So in other words, every polynomial has a root and completely splits. That is called complete splitting. And so C is called algebraically closed. Okay, so this is the definition of algebraically closed field. that any polynomial completely splits or degree d polynomial has d roots in the same field. Yeah, okay, so we'll continue next time. Any questions? Have you seen the proof of this?
Complex analysis.
Yes, but complex analysis is very heavy. So how short is the proof or how long is the proof? The proof is actually very short. The proof only requires this modulus operator, a complex number, and you want to compute its norm basically. The proof is just uses norms, uses the norm and the relationship between coefficients of your polynomial and the roots. Okay, so it's actually a very simple proof, but obviously tricky and fundamental. So that also I leave as an exercise. So next time we'll start factorization algorithms over finite fields.